Hello, this is an ambitious problem. A closed system is given, a tank that contains air, and it goes from state 1 to state 2 as the air is heated. We are supposed to find the heat transfer, but the interesting thing is we are supposed to treat the air as a pure ideal gas in part a binary mixture of two different gases, oxygen and nitrogen. Again, and at C, again a mixture, but this C is using NRG model, which allows as many gases as you want in a mixture. A binary mixture only allows two gases. And finally, a chemically reacting mixture. In other words, oxygen and nitrogen are being heated. It's possible that they may react to produce some NOx, like nitrogen monoxide, nitrogen dioxide, etc., known as the common term is NOx. So this is a very ambitious problem. The background, of course, the IG model is covered in chapter 3, uh, and then the binary mixture is covered in generally chapter 3 and 11, a general mixture in 11, and the equilibrium model for mixture, where chemical reactions are allowed to take place, is covered in chapter 14. So let's begin. I have already to reduce the time demand. I've already started the test apps, but to let you know exactly what we'll be using, obviously, we are supposed to find properties of a closed system, which is a system state will be ideally suitable for that. And we are going to use different models. So for instance, for perfect for a pure gas, we'll use the IG model from here. For binary mixture, we'll click here, and for a general mixture, we'll go for the NIG model, and finally, the reaction with possibility of reaction, we'll go to the ideal gas equilibrium model. So I have already launched those separately, so I'll go directly there. So this is the system state test step with ideal gas model. So let's write down what we know. The state 1 of air is already selected. We know the temperature is 300 Kelvin, mass is given as 10 kg, and pressure is given as 100 kPa. So state is calculated. State 1 is done. For state 2, we know that the mass must be equal and the volume must be also equal. It's a rigid tank, and the final temperature is given to us as 3500 Kelvin. So state 2 is easily calculated. And we go to the IO panel, where I already typed the equation in. Q in must be equals mass times change in internal energy. A calculate brings up the result, which is 28843, or 28.84 million joules. So let's write down summarize the results here. So for the ideal gas model, we found that the final pressure is 1166 kPa and Q is 28.84 million joules. As you can see, the final pressure is 1166. So I have already compiled the results, but you can go and verify. So let's move ahead and now use the binary mixture model. Recall the binary mixture model is launched. If you look at the different models, the pure gases are here, perfect gas, ideal gas, and real gas model. And the mixture models are separated into binary mixture and general mixture. And by clicking IG plus IG model, you end up here. Okay, it's by default mixture of air versus air, but no, we will have oxygen and nitrogen. And the mixture is defined by the mole fraction of, notice XA and YA defines the mixture of binary mixture. One of them will do. X is the molar mass, mole fraction, I'm sorry. No. X is the mass fraction, Y is the mole fraction. So if you go over Y, it tells you the mole fraction is given to us in this problem is 0.21. And the temperature is 300 Kelvin, pressure is 100 kPa, so state 1 is calculated. For state 2, we know mole fraction is, again, oxygen is 21%. Mass and volume must be equal, so we can calculate the state. Again, the final pressure is exactly the same. If you go to the IO panel and write down the equation, Q in must be equals m times m1 times u2 minus u1. That equation remains identical, doesn't change the energy equation. So we get 29.88 million joules, which I picked up and wrote down here. So we have got answers for the pure IG model, and now I have a binary mixture model. And now let's go and take a look at how we solve the same problem using a general mixture model. I know we don't need to, but this is a much more versatile. Again, we launch it by going to the NIG model, which is general mixture model, and we go to the NIG model here, and that will launch something like this. As you can see, we are in the composition panel, state panel and graphics panel, IO panel. These are all identical. The only new thing here is the composition panel, which should be very intuitive to use. And you will see how the general mixture model gives us a lot more information than the binary mixture model. So let's compose the mixture. In this case, is percent by volume is known. Oxygen is 21% by volume. Nitrogen is 79% by volume. So just the proportion of oxygen and nitrogen, we just add. Our mixture A is ready, and you can see that it is giving us a pie chart of how the mixture looks like, and a molar composition. Mixture A is made of 21 moles of oxygen and 79 kilomole of nitrogen out of 100 kilomole in this case. Okay. So we go to the state panel. Now that we know mixture, we notice that mixture A is picked up here. We could make a number of mixtures, just like fluids appear here, air, oxygen, nitrogen. Over here, only we'll have different mixtures. Of course, you can create a pure gas by just adding one gas, calling it mixture A or B. Okay, so again, let's write down what we know, 300 Kelvin, and the mass is 10 kg. So state 1 is perfectly found. And notice that the partial pressure of oxygen and nitrogen are displayed here, as are many other partial properties which are covered in chapter 14. Okay, you go to state 2, again is the same mixture. We don't worry about that. Oh, sorry, we don't know the pressure, but the temperature is known, 3500 Kelvin. And mass is equal and volume is equal. And that gives us the pressure exactly the same. And of course, we are treating, the answer must be identical to Q in must be equals same as the binary mixture model, because nothing really changed. Oops. Q in M1. Oh, just 1 second. Did we adjust the mass? Did we write down the mass correctly? Yep. So mass is 10 kg times U2 minus U1. So it's 29.88, exactly what we got for the IG model. So these two models has to agree, because essentially this is a binary mixture and this is a general mixture, but they cannot produce different answers. Okay, finally, let's try to solve it using the most complex of all models, which is the IGE model. It looks very similar to NIG model, but it is IGE means ideal gas equilibrium model. In other words, in this case, instead of calling it a mixture, we call it a reactant. So let's define our reactant by percent by volume again, 21 meter cube of oxygen and 79 meter cube of nitrogen, or percent nitrogen by volume. By volume and mole, they are proportional, you know that. Mole fraction and volume fraction are identical according to Dalton's theory. So we got our reactants very precisely defined. Now let's go and figure out the products. Well, when we go to the products, we notice that all of these are possible. The test tab automatically picks up, because we are using oxygen and nitrogen, we know the atoms needed are O and N, and these are the different molecules that are in the database. So we can just pick and choose. For instance, smog is made out of oxygen and nitrogen reacting in a car. So you can, in fact, figure out what is the biggest composition of smog by selectively choosing. So let's choose all of them, and we can take a look at what is the most number, which is the highest concentration out of all that. So we are selecting all this by clicking here, the select all components, and then adding them. Of course, we could select one and remove that if you want. Like that, we can add or remove a gas. As you can see, the products we have listed all these products, in this big list. And this is the room for the pie chart. We don't know the pie chart yet because we don't know the composition, exact composition. We have defined the products. Define means we have said what are the possible components, but we don't know their amount. And all the atoms that we need to cover have been covered. So let's go and calculate the state. Notice that here only pressure and temperature are allowed. We cannot enter every property. This restriction will be gradually removed because this involves a lot of computation. So anyway, state 1 is very simple. Nothing changes. Recall that the volume of the tank is about 8.648. Okay, for state 2, notice that we cannot write volume 2 equals volume 1. But we do know temperature, we know mass, and let's take a guess for pressure. Let's say we say it's 1100. And now if we calculate, let's see what we get. We get a volume of 9.43, way more than, of course, the composition is calculated, but the volume is wrong. The volume is supposed to be 8.64. The rigid tank cannot change in size. So we try to iterate here. So 1100 kPa produced this. So the pressure must be higher for the volume to be smaller. Let's say we say it's 1300. We get a 7 point. So we are in the right track. It is now the volume is even higher, still higher. So let's keep on iterating, and let's say it's about 1200. And that's just about right, 8.643. Again, it's a very non-linear kind of iteration. So you got to check different values of pressure until you get the correct answer, which is 8.64. That's about right. It is 8.648. So that's close enough. And notice the composition has been found, and this is displayed here. All the gases that are produced here, and if you go to the I/O panel, we can calculate Q in as M1 times U2 minus U1. This should be, the heat transfer is about 36.6, way higher than before. 36.5 I wrote down. Okay, this probably is a better guess. So you can see that because of chemical reaction, the answer can be quite different because now we have different properties of gases because of the reaction. So I'll pause here. The purpose here was to illustrate a gradual introduction of complexity into gas model.